Hello, everyone. Good to see so many of you here. Really delighted to be talking to you about building resilience in your systems through kiosk engineering. So I'll touch on what, why, and how, a bit of principles behind kiosk engineering, and how do you go about building resilient systems and adopt kiosk engineering for that. So everything fails all the time. That's the quote from Werner Vogel, CTO of Amazon. And I love that quote because it allows us to embrace failure as a natural occurrence, right? Everything fails all the time. You try and do a demo in a live event, it doesn't work, so you have to kind of expect that. So what I want to talk about today is why I'm going to talk about AWS WellArchitected Framework first is creating software systems, creating services or technology services, applications, whatever it is. We have drawn parallels from manufacturing industry. If you're going to construct a physical building and you want the foundations of that building to be strong, right? Similarly, you don't want your technology systems or applications to fail because if your building is not strong enough, it doesn't function. Your software systems are not built to be resilient, built to be fault tolerant, then your systems aren't going to do the job you expect them to do, right? So how many of you are aware of the well-architected framework? I'm expecting a lot of you. Yeah, okay. So I'm not going to go deep into this, but just to bring everyone on the same page. AWS has compiled a set of design principles and architectural practices. Having worked with thousands and thousands of customers, building this over many, many years, and having worked across a variety of business verticals, right? So this is what AWS WellArchitected Framework is. It's compiled under 6 pillars. You may all be aware of that. Without going deeply into these, why I have brought that up is because it's relevant to today's topic, reliability. So in the reliability pillar, let's first cover what is reliability, right? The ability of your application or service to be able to serve whatever it's been built for consistently and correctly can be summarized as reliability, right? The other supporting pillars, the operational excellence and performance efficiency, also form part of your resilient architecture, in building your resilient architectures. Performance efficiency, the ability of your systems to use the resources in the most efficient manner, as well as operational excellence supports your developers' function to be able to monitor your systems and services and be able to alert the developers to remediate whatever the situation is, right? And to constantly improve your services and applications. So under the reliability pillar, there is the question about injecting failures into your systems to be able to observe how does your system respond to those failures. So the practice of using this fault injection or failure injection into your test environment is also better known as chaos engineering. So I'll briefly touch on what is it and why are we interested in it and how we go about adopting those, right? So chaos engineering is the process of stressing your application and observing how your system behaves and then applying those improvements to your system and build that reliability over time, right? So what we are doing is it's an approach of learning about your system behavior when subject to scientific experimentation and trying to find that evidence of where your system might go wrong and put the improvements in your system. So why chaos engineering is becoming more prominent or important? With the rise of microservices, distributed services being built, developers working parallelly, developer teams working parallelly, deployment of the software becomes a little bit more complex than it used to be previously. So while individual components work fine, when put together, when integrated, you may come across some unexpected faults or failures. How many of you have deployed or released a feature in production on Friday evening and relaxed over the weekend, right? I am certainly guilty of feeling, oh, I hope that this weekend goes fine, kind of scenario. So what we're trying to say here is that the failures can cause sometimes costly outages for companies, and sometimes it may even affect the bottom line. For example, if Amazon.com has events such as Black Friday sale or something on that level during Christmas period or whatever, even the smaller time frame outage could actually impact the business, right, heavily. So it's not waiting for that failure to occur in production is no longer a choice, no longer an option. So more and more engineering teams are having application uptime as a key indicator, key performance indicator for the development teams. And hence more and more companies are tuning into chaos engineering. So there are 5 phases of chaos engineering: understanding the steady state of your application or the service you're building, and we make an assumption about that steady state, and then we articulate a hypothesis about that steady state, run some experiments, and verify those results, and finally learning from those experiments and improving your system. In order to build resilience into your systems, as we've been talking about it, we need to put our systems to test, right? You need to understand what are the scenarios your system might fail, maybe initially certain set of scenarios, and around those scenarios build the experiments that you want to conduct. So the kind of chaos experiments could be around physical server going down, or it could be software failure. For example, it could be malfunctioned response, or it could also be network spike or increase in traffic that you didn't anticipate, and so on. So let's look at the tooling that's available for us to adopt this and make it a practice in our DevOps practices. So this isn't an exhaustive list of all the tooling that's available, but I just wanted to draw a bit of a history around how it originated and so on. So in 2010, Netflix engineering tools team have created Kiosk Monkey to test their system's stability by enforcing failures or by removing, shutting down certain servers in their Netflix architecture. Later on in 2011, they've created Simian Army, which gives them a bit more, a lot more faults that they can induce into their systems rather than just terminating the EC2 instances, right? And as the adoption of these products and tools increased, people wanted to be able to use it as an API. So the toolkits, Kiosk toolkits emerged, which gives you a CLI to be able to inject these failures into your systems. That meant that developers could adopt it and put it probably in their CICD pipelines as well. And a variety of other products. Kiosk Mesh for Kubernetes is a very powerful Kiosk engineering platform, which directly can be deployed onto the Kubernetes cluster itself without having to change your application's code or deployment code or anything like that. So it makes it a little bit easier to install it and run the experiments. Then there is Gremlin in 2019 launched failure as a service. That's the first company. Gremlin is the first company which created failure as a service. Started off in 2016, but it got deployed or launched in 2019. Actually, back in 2009, Colton Andrews built fault injection in service in Amazon, and he went on to co-found this company as an offshoot as well. Gremlin actually has a comprehensive set of tooling, and not just limited to a particular cloud provider, which is advantage and is available in AWS Marketplace. So in 2021, Amazon came up with AWS Fault Injection Simulator for making it easy for the developers who are building these services in AWS to create experiments, to be able to run Kiosk engineering experiments much easily on AWS. So FIS is a fully managed AWS service designed to get started easily, applicable for real world conditions, and it really embraces the philosophy of safeguards and reducing the blast radius to a certain amount or to certain resources or to certain percentage of fault that you want to induce into the system. So you can inject faults into EC2, or you can inject faults into ECS, EKS, also API gateway, for example, throttling, increasing the amount of throttling for the API gateway requests, as well as API not available sort of faults. So these faults come these faults occur at the control plane level, which aren't otherwise possible for you to set these faults with external or other tooling available. So we have 4 main components in FIS: actions, targets, experiment templates, and experiments. Actions are the faults themselves, and targets are those resources on which the faults are going to be induced. And then you have the experiment templates. It's a template that where you create, this is the action, this is the target, the action has to work on, and that's the template. So one or more experiment templates can be put together as an experiment. So let's talk about how to recover from these faults in AWS. So let's take this example where you have a 3-tier architecture hosted on AWS. The web tier is built on top of ECS, Elastic Container Service, and receiving traffic from the internet. The middle or the application layer is also hosted on ECS, receiving traffic from the network load balancer from the web tier. Backend being Amazon Aurora. So here is an example. Probably you won't be able to see it that clearly. That's the console for FIS, where on the left-hand side you have your templates and experiments. What I have here on the screen is some of the experiment templates that are for creating availability zone failure, or for EC2 failures, or for memory, causing memory stress, or CPU stress, or network spikes, and so on. So how can you create these easily? So basically, behind the scenes, it uses Amazon system management commands to cause this stress. These are pre-built actions with which you could create templates easily. So let's say in our first scenario that I showed earlier in the architecture, if you want to cause the CPU stress, then what would be the hypothesis for that scenario? The hypothesis would be if the CPU utilization for the compute resource were to be stressed, then the availability of our website is still intact and is not impacted, because we have built is auto-scaling capability, or we've surrounded an auto-scaling capability for the service to not go down, right? So if you select the CPU stress template and run the experiment, the action behind the CPU stress would be an SSM command or systems manager command to trigger the fault. Similarly, you can conduct similar experiments for network packet loss or an availability zone failure, like here, right? What we're trying to do here is mimic an availability zone failure where 50% of the resources are not going to be available if you have equally distributed your services into availability zones. And not having the availability zone also means that it causes the RDS cluster database failover. So in this case, the hypothesis for our scenario is 50% of our instances going down is not affecting the availability of our website. So running the experiment is going to terminate 50% of our total EC2 instances. You can follow similar steps like I was showing in the previous slide, where you had the FIS console. You can select the template you want for the experiment, start experiment, and you can observe the change of the state of the experiment as well as the impact that it's having on the resources that the fault has been introduced to. You can build CloudWatch dashboards for monitoring the failures. So where the blast radius can be reduced is if you thought that the experiment is taking longer or experiment shouldn't have impacted certain EC2 instances which were based on tags, then you could you could use CloudWatch alarms to shut down the experiment or stop the experiment as well. So now that we've learned how to conduct the experiments using FIS, it's not sufficient to run it once and forget it, right? Because let's take a look at how to make this a reality. One way to do this is to test your systems through game days. I will give you an example where at the beginning of product development, during the initial phases, the amount of data replication required, we assumed that the data will replicate in a certain time. So that is the steady state, let's say. Sometimes you don't anticipate how much data is going to be created over time. And if you don't conduct those experiments again and again, then your steady state assumption of data replication within a certain time will not be true. So that is another reasoning why we would conduct these game days or conduct the experiments to inject faults on a regular basis. So you can get a team of cross-discipline team or a team that hasn't used your system before, create roles as to what they are going to do, set up the experiments or ask them to run the experiments, learn from those experiments and implement those changes, I guess. Making them part of CICD pipeline is another way to ensure that you aren't breaking something, you aren't introducing any performance bottlenecks, and so on. Finally, I want to leave you with the quote regarding kiosk engineering. It isn't about creating kiosk, it is about bringing the kiosk that is inherent in the system visible to you so that you're able to fix them and improve that system. So make sure you do the kiosk in test and staging environments before you introduce to do it in a production system. Maybe you should choose to do it in a quieter period as well. So I invite you to start testing your systems through the tools and services that are available that we discussed. Gremlin website has a really good comparison of what tools will be right for you. So that's a good comparison across a wide variety of the tooling that's available there. I'll share some resources here. If you would like, you can, these are workshops publicly available. You can take your time to experiment.